This lesson is on the formal definition of a derivative, and we will be needing you to know all these steps, although we will be learning some shortcut rules in the future. The first thing that you need to remember, and as I've mentioned in previous videos, that a derivative is the slope of the tangent line and also the instantaneous rate of change. So anytime they ask you to find the slope of the tangent line or the instantaneous rate of change, you will be doing these calculations. The nice thing about this is we can find the derivative at a point, which we will be doing some today, or at all the points on a graph, which will make us another function. And you had some practice with that with the distance versus time graphs creating a velocity versus time graph. So it does, if you plot every single slope, make another function that we will be using. Another thing that's interesting about derivatives is that several different mathematicians came up with derivatives, and we use multiple representations because of that. So some different ways that they ask for derivative, or you can denote that you're trying to find the derivative. We have delta y over delta x, which should resemble your slope, and dy over dx. Also, it's kind of based off of that delta becomes a d. But with y's over x's, it should remind you of your slope formula, and again, derivative is slope of a tangent line. This notation over here, d over dx, again, similar, reminiscent of that, and then we use the function notation with it, or just d sub x and y, which is kind of a play on this one over here as well, noting that that's derivative. Some of the most popular ones that I have skipped over here are y prime and f prime of x. Those are just popular, and they're easy to do real quick when you're learning all your rules. So regular y notation or function notation. But again, you need to be able to recognize all of these notations as requesting you to do the derivative. Okay, now we move to the definition of the derivative. And this is the mathematical definition, and this is what we'll be using today. And so I want to first show you where that comes from. Okay, so we're going to look at this. We'll say this is our function f, and we want to look at a specific point on there and estimate the slope of that tangent line. So that point has an x value that we don't know and a y value that is the output of that x value, f of x. And so that's how I can talk about that point without having any specifics. So what we do is we say, okay, well, the slope of the tangent line here is really close to the slope of the secant lines that you can draw around it. So let's go some distance ahead, and we'll call that distance h, to a new x, which would be x plus h. Because if you knew that x was 5 and you went 3 ahead, you would be at 8. You got that by adding. So this x plus h is h ahead of x. So our point is up here, and that point has an x value of x plus h. So its y value would be f of x plus h, its output. And we are going to think about the slope of the line between them, because the slope of that line is very close to the slope of this tangent line. It's just a little bit less steep in this case, but it's close to it. So if we do the slope of the line, the secant line between those, we have y minus y, so f of x plus h minus f of x, over x minus x, which would be x plus h minus x. Okay, well, if you combine like terms on the bottom, you're just left with h, and you'll notice the top is the same as this. So this fraction becomes this. Well, what does the limit have to do with it? Well, now you know what h is. The limit as h goes to 0. If h is smaller and smaller, right now, I said maybe it's 3. Well, if I moved my point closer, my h value would be smaller, And the closer I get, the better that slope is going to be, the closer it's going to be to that tangent line. So we are taking the limit as h goes to 0 so that we can get our 2 points closer and closer together and get that slope as close as possible to the tangent line. And by taking that limit as h goes to 0, we can get the slope of that tangent line. I would really like for you to understand what I'm saying, and if you need me to explain it personally to you, then raise your hand and call me over. If you don't, for today, work on just learning to use and know this definition. But again, I would really like for you to understand where it comes from. Okay, for our first example, we are going to use f of x equals 2x minus 5, and we are going to use that definition of derivative to find the derivative f prime of x. So each time you do this, you need to make sure that you put the limit as h approaches 0, because sometimes people get caught up in the algebra so much they forget that. But when you're doing this, you need to show that limit until you have taken the limit. Otherwise, it's going to be partially incorrect. So the first thing that you have to do is do f of x plus h, which means I'm going to plug x plus h in to my f equation. So 2 parentheses minus 5, and in place of that x, you're going to put x plus h. Then you subtract f of x, which is the whole thing, and you need to put a parenthesis around it because otherwise you will get the signs wrong. And then it's over h. And again, you want to go ahead and work on this math, but make sure on the next line you bring down that limit as h approaches 0. Okay, now I'm going to distribute my 2 through, so I get 2x plus 2h, bring down the minus 5. Distribute this negative through. If you need to treat it like a negative 1, write a negative 1 in, but I get a negative 2x and a plus 5. And again, that's what you would be missing if you had forgotten to put the parentheses around there. So that negative times the negative makes it a positive. And I'm still not done. I'm not ready to take the limit yet, so I'm going to put limit as h approaches 0. And then on this next line, I'm going to start canceling out the positive 2x and the negative 2x, the negative 5 and the positive 5. And that leaves me with a 2h on top and an h on the bottom. And those cancel out. So I have the limit as h approaches 0 of 2. And if you'll remember, that's one of your famous limits, just your horizontal line. So as h approaches anything, the answer is 2. Now, if I were to ask you to find f prime of 3 in this situation, or f prime of negative 3, since that limit as h approaches 0 of 2 was 2 and there was no variables, again, this would just be 2. Any number that I plugged in here would have an output of 2. Okay, for our second example, I'm going to do something with a little more work to it. So we're using a function that has an x cubed and an x, and we are first going to use that definition of derivative to find f prime of x. And so I need to start with that limit as h approaches 0. Then f of x plus h means I need to put x plus h in for both of these x's. Okay, once you're at this point, you want to subtract f of x, which is the whole thing. So x cubed minus x, and then it's over h. I have not taken the limit. I have a lot of algebra still to work out, so writing your limit down. Okay, this x plus h cubed, you either need to come over to the side and write x plus h 3 times and multiply it all out. You can multiply 2 at a time. Or if you know the shortcut using Pascal's triangle, then you can use that shortcut. I'm going to use Pascal's triangle and maybe jog your memory on that. Since it's cubed, our coefficients are 1, 3, 3, 1, and then we have x that we are cubing, squaring, and then just x. And then h comes the other way, h cubed, h squared, h. And then because it was a plus, everything gets a plus. So again, you may remember how to do that, and if you do, that's great. If not, you can FOIL 2 at a time and then distribute the other through. So this takes care of the x plus h cubed. I still need to distribute the negative in and get negative x and negative h, and then distribute the negative in here. So negative x cubed and positive x. Now I'm still not ready to take that limit, so bring that down. And I'm going to cancel whatever I can. So I have an x cubed, 1x cubed, and a negative x cubed. Those will cancel. I have a negative x and a positive x. Those will cancel. And I believe that's it. So I'm going to write down what I have. I have 3x squared h plus 3x h squared plus h cubed, and then minus h, and it's all over h. Now, to our next line, you can think about factoring an h out of the top and then canceling, or you can just think, okay, I've got an h in everything. It's like reducing a fraction, so I can take that h out of everything. So I'm going to drop h from each one of these things. So I have 3x squared, the h is gone, 3xh, because I can only take one of them, h squared, and then when I take that away, I still have a placeholder of a 1. But the h on the bottom is now gone, so if you need to, put a 1. But, and if you want to clean that up, you have limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 1, because you really don't need that one fraction. Now you are ready to take the limit, because you can no longer get a 0 when you plug in on the bottom. So you can plug in 0 for your h's, which will give you 3x squared plus 3x times 0 plus 0 squared minus 1, and that will give you 3x squared minus 1. This is your derivative, and as I mentioned in the beginning, sometimes you get a function which is, if you graph it, represents the graph of all of the slopes plotted from the original. And we can use that to find the derivative at 2. So f prime of 2 would mean that I would plug in 2 into this equation. So I would get 3 times 4, which is 12, minus 1, 11, and that will be our answer. That will be the slope at the particular point where it has an x value of 2. And again, this situation was a little bit different than the first example, because in the first example we came out with a derivative that was just a number, and it was a horizontal line that would represent that graph. And in this case it was a function, and so each value that I plug in, like if I wanted f prime of negative 1, I'm going to get a different output. F prime of negative 1 would be 3 times negative 1 squared minus 1, and I would get 2, and that would be the slope at the point where the x value is 1 on the original graph. So that concludes this part of our definition of derivative lesson.